Okay, so let me briefly talk about microinverter. We have a guest speaker on this topic next week uh, from a company called Enphase, which is one of the pioneers in this microinverter space. In fact, they were the first in that space. There are many copycats after them, but they were one of the first people to realize this idea. The story I've heard is, the founder was working in his ranch, and he realized that one inverter for the whole system doesn't make any sense. Why not we have multiple inverters for one for each panel, right? So before getting to that, let's just understand some basics of inverter. So why do we need inverters? Right? Because the sun is DC, and the power which we get in our homes, thanks to Nikola Tesla, is AC power, and depending upon which country you live in, US, I think it's 120 volt, 50 hertz. If you go to, say, India, it's 220 volt, 60 hertz. Actually, more places it's 60 hertz than 50 hertz. And to convert this DC power into AC power, you need an inverter. And the most simplest way I can explain an inverter, it's basically a supercharged capacitor, or not a supercharged, but a big capacitor which essentially stores the energy which is coming in from your panel. And then you have this system of 4 switches, and what you do is essentially using some kind of electronics, using some simple transistors, you connect these two. You connect these two such that you get positive polarity on these lines, and then you open these up, and then you connect the other two, and that reverses the polarity, so it flips the polarity. And using the energy stored on this capacitor, you generate this AC signal. And this switching is done using circuitry made out of transistors. Okay? So this is the simplest way a inverter works. Now there are regulations on these inverter systems as to how they can connect to the grid. So a lot of times you connect these inverters directly to the grid, and you usually place like a disconnect box at the panel level. So if something is wrong at the panel, you can disconnect it. You place another switch at the point where you're connecting this to the grid. And in US, the law is that if there's something wrong with the grid, all of the panels have to essentially completely get off it. So this box has to be smart enough to understand that if the frequency of the grid is going up or down, they ask solar utility plants or anybody who's feeding into the grid to essentially get off the grid if the grid is starting to fluctuate. Europe, on the other hand, the regulation is that if something is going wrong with the grid, you want them to remain connected. They think that the distributed panels, they can actually help in restoring the grid. So depending upon which country you're in, again, there are different regulations on how you connect into the grid. But the basic is the same. You have this one switching circuit, which is switching this capacitor and generating this AC signal. And then many times, to maintain the integrity of that signal, you have that filter as well, that if the frequency is changing, you filter it out, and you want to maintain that constant frequency you want to feed into the grid. Okay, so earlier, these things used to be all connected into these panels. It used to be connected in series, and there was this whole field of string matching these panels, and there used to be a central inverter, and again, it used to come at a fixed capacity. Let's say this inverter is at for a capacity of 4 kilowatt or 5 kilowatt, and you would string connect these panels such that you generate output of anywhere between 300 to 600 volt, which is pretty high, and that is needed if you want to produce power at say 240 volt, which is most of the other countries outside US. So again, things like we just discussed, like shading, right, or a bird pooping on the panel. So it will not only degrade one panel, but it will degrade all the string of the panels which are connected with each other. So you used to get losses like anywhere between 5 to 25%, just because of these panel mismatch and all these issues. Okay. So the solution is essentially placing this inverter on each of these panels, or what is called a microinverter. And the reason it became feasible was thanks to Moore's law, the electronics needed to essentially cause this conversion became cheap. Earlier it didn't used to be that cheap, so it was not practical to replicate that electronics on each panel level. But now it has reached a point where it's increasingly becoming more economical to do it. So there are two kinds of these microinverters. So one is the one which converts this AC power, this DC power into AC power at each inverter, at each panel level. So it causes this DC to AC conversion at each level, and the pioneering company for that would be Enphase. There are many other companies which are similar to that. The other one is this DC to DC converter. So what it does is it does not causes this AC conversion at each panel. It just for each panel it tracks the maximum power point, and it generates that DC power which is optimized for that panel, and you feed that DC into a thing at the for the whole installation or for a system level. And these are, if you're familiar with circuits, these are these buck boost converters which convert DC to DC, and there are several companies which are active in this area as well. So what you save in this case is that you save on that switching electronics which is needed at each panel level. So these DC to DC ones are typically slightly cheaper as compared to DC to AC at each level. And the other thing which you need to keep in mind if you're like converting into AC at each level is that all of these AC conversions have to be in phase, right? So you have 3 of these over here, and if 2 of them are completely out of phase as compared to the first, you'll generate no power, right? So a very important thing to maintain in this conversion is phase matching. And the way these individual panels communicate through each other is through this power line itself. So they use this power line not just for transmitting power, but they use it to communicating with each other as well. Just like you do your telephone, the power for that. If you do have a landline still, and actually if you live in Stanford, you might have a landline, right? So the power for that phone comes through the same line which is transmitting the signal as well. So similarly, these panels or these microinverters, they communicate with each other through the power line which is connecting them. Right. So it's not all rosy. There are some challenges with these microinverters as well. So let me take your opinion. So I've mentioned a few of them, but let's discuss what are the pros and cons of replacing this central inverter with a microinverter at the back of each panel. Higher cost, okay. So cost higher, okay. What? So that's a pro, right? Okay. Reduced shading. No requirement on panel matching, right? Okay. What? That's actually a very interesting point. So failure rate, one of the more common causes of panel or solar installations failing is inverter issue. It's not the piece of silicon is pretty robust, right? There's nothing much which happens here. The thing which most commonly fails is a central inverter. So what you're saying is what Dan is saying is that this would be better for failure issues. But the thing is, if this fails, I can quickly go and replace it, right? This is located on the ground. If this thing fails, I'll have to climb up my roof, figure it out where it's, first of all figure out which one is failing, and then go and replace it. So you're right, let me put it down. This is a pro for that is, let me put it both. So, I mean, pro for this is failure. Pro for this is essentially easy access, right? Yes, I mean you could do both depending upon how skilled you are, but yeah, I mean over here you might be at the danger of causing harm to yourself. Over here you might not be. Yeah, but both are. I mean, you could do both yourself, or you could do neither yourself. Yeah, but okay. Yeah, that's the point. Yeah, so I can essentially over here I can track the maximum power point of each of these. So I can do MPPT tracking on each of the panels versus doing it on a system level. Okay, so this is most of what I had in mind. So you don't need parallel matching. You can optimize for each panel, but it comes at the expense of higher costs. So typically my panel costs have fallen less than $1 per watt. But if I do add this inverter, it adds something like 30 to 40 cents per watt of peak power. And the other thing is not that easily accessible. And these costs have not fallen as rapidly. The panel costs have fallen pretty rapidly, but the microinverter costs have not. Okay. So this is a slide from this company Enphase, from which we'll hear next week. So they make these very nice inverters. So they go at the back or behind each panel or two panels at a time, and then they communicate with each other. They also communicate with the central box, and then the central box essentially has an Ethernet connection to it, and you can it's pretty cool. You can browse your house, how it's performing from your phone, from your browser, and see how the panels are working, and if one of them is going bad, it can send you a notification. So it's pretty nice, but it comes at a cost. Okay, so the other intermediate solution was doing this DC-DC thing. So you can still obtain the advantage of tracking your maximum power, and it's less complex. But it still requires, it adds to your cost. It still requires communication between these individual things. Okay. So now, one of the things I just want to mention, and I want to give you enough resources on, is on the grid issues. So countries like Germany, where on a sunny summer day, up to 50% of their power is produced by solar panels or a combination of solar panels and wind, they are starting to experiencing these issues where you have these existing AC grids, right? And they are optimized for taking power from known sources, which can be pumped up and down depending on your will. So if you have a nuclear plant, or if you have a coal power plant, or if you're especially if you're hydrodynamic plant, right? You can turn it on and off. You can regulate how much it feeds into the grid very quickly, right? Versus sunlight, it depends. It's a good thing, but it's a finicky source, right? You might have a cloud cover coming in on one whole region, and suddenly that amount of power it's feeding into the grid, it fluctuates, right? And wind is even more finicky as compared to solar energy, right? So suddenly it starts blowing, and you have a lot of wind coming on the shores, and it's generating this power, and suddenly it dies out, right? So your grid, it becomes a very easy thing that can break down, and these issues are now starting to get noticed, especially in Germany. So what they have done is, what they are planning to do is essentially this existing AC grid, which is shown by this yellow line, right? So these are not the best way to take solar power or take this renewable power from one place to another. A much better way would be, start from the place where you are generating it and take it to the place where you need it to take on a point-to-point connection. Just like, you share files on a peer-to-peer basis. You want to take this solar power using these ways. And what the system they're designing for this is, again, it's using DC instead of AC, and it's a high voltage DC system. So it's again going back to the time of Edison versus Tesla, where you want DC versus AC power. And there are many challenges with it. Especially it's very hard to turn off these lines. If to turn off these high voltage DC lines, you need like big rooms of these converters, which will essentially think about the overall capacitance of this, overall system capacity of this line, which is transmitting this huge amount of power, and you need to turn it off immediately if something goes bad. So there are a lot of issues, but this is a hard topic. There are other experiments in Europe. This is, for example, an island near the coast of Sweden, where they're trying to experiment with all these different kind of sources. Each has a mind of its own, and how do you maintain the integrity of the grid? And for this renewables, a lot of time it's the amount of power they generate, you cannot control it, versus say a hydroelectric plant where you can just tune in your turbines and you can match the capacity of the grid. So I want to give you good resources to read about it. So what I've done is this one place it has a combination of a lot of these articles about smart grid, and then I've given you some more resources, issues we talked about, recombination, etc. You can read chapter 2 in Fonash's book about these cell design, how the bad cell affects the overall module. I've picked most of that material from one of our reference book, and then the issues of shading, etc. are more explained over here. So let me now actually jump gears and let's talk a little bit about problem set. Okay.